Hello, my name is Margalit, and the name of the work is Verifying Observational Robustness against the C11-style memory model. This is a joint work with Lahav, and we are both from Tel Aviv University. Let us recall the simple memory model of sequential consistency, where if we have a concurrent program, each thread gets executed on its own CPU, and the various CPUs take turns accessing a shared memory location, where only a single CPU may access the memory at any given time. In practice, hardware implements weaker memory models that trade off consistency for performance. And what we know is that all the behaviors of the program when executed under a weak memory model are a superset of the behaviors of the program when executed under sequential consistency. We also know that verification of programs under weak memory models is difficult, both in theory, where the complexity can be very high, or the problem is not even decidable, and in practice, and I will mention an illustrative example of Peterson's algorithm later. And what we would like to do is verify programs assuming sequential consistency. This means that if we prove some property about the program and verify its correctness under sequential consistency, we will achieve verification under the weak memory model. And what is this property that we need? The property is called robustness, where all the possible behaviors of the program under sequential consistency are the exact same set of behaviors of the program when executed under the weak memory model. And in this work, we develop a method to automatically establish robustness of programs against a weak memory model, and specifically, we focus on the memory model of C11 that was introduced in 2011 and provides a spectrum of memory accesses and trade consistency for performance. Our main contributions are showing that the standard notion of robustness against C11 is decidable and p-space complete, and develop a tool called Rocker that, given input programs with C11-like atomics and non-atomics, produces verification problems that assume sequential consistency. This means that we check for the robustness of the program against C11 while actually executing the verification under sequential consistency. And this problem is fed to the spin model checker and allows to see whether the program is robust or not robust. In addition, we introduce a novel, weaker notion of robustness called observational robustness that we require for some algorithms, and develop a method for checking whether a program is observationally robust or not. And this verification is sound but not complete. Previous work mostly targeted specific hardware models, especially the x86 TSO, and our work from last year regarding the release acquired fragment of C11. Now, unlike release acquired accesses that support massive passing idiom, relaxed accesses do not. Let us consider the example, and this is going to be a running example, where the first thread writes the value 1 to x and then the value 1 to y, and then the second thread is reading the value of y. And it is allowed to read the value 1, and everything is fine. But under the C11 memory model, when using relaxed accesses, it is still allowed to read the value 0 for x, since no synchronization happens. So let us see how this happens. Now, although the C11 memory model is not formulated as an operational model, we can still think about it in terms of operational semantics that look like this. We have a state that is consistent of the program state, which is going to be used regardless of the memory model, and contains the various registers and program counters of the program, and a memory state, which under sequential consistency is going to be a simple data store. But under the C11 memory model, it is going to be an execution graph that consists of all the events taking place during the execution of the program, starting from the initialization events of initializing the memory, namely of 0 to x and 0 for y. And we can take a step as long as the graph is going to be consistent. And the full definition of consistency is available in the paper, but we do not need to worry about this for the rest of the talk. Now, let us see what happens when we write the value 1 to x. we create a new event in the graph of having the value 1 written to x, and this is executed after the initialization events. Next, when we write 1 to y, we create a new event in the graph that is executed after writing 1 to x. Now, when the second thread is going to read the value of 1, it has to justify the fact that it is reading the value out of somewhere, and namely, it is going to say that it read the value 1 that was written in this write of 1 to y. Now, when the second thread reads the value of x, since no synchronization happened, it is allowed to read the value 0 for x from the initialization. But while it is C11 consistent, it is not sequential consistent, since for us to be able to read the value 0 for x here, it has to be before the value of x was overwritten by writing 1 here, which is executed before writing 1 to y, which is executed before we can read the value 1 for y, which is executed before our read of x. So we have this cycle from this induced relation, showing that the graph is not sequential consistent. Now, since we don't have synchronization, we cannot reason about programs and we cannot program. So in order to restore correctness, and we have the use of fences, and by adding a fence release here between the two stores and the fence acquire between both floats, we forbid this behavior of reading 0 for x, since these two fences introduce synchronization between the threads, and therefore this graph is not C11 consistent, since we cannot read the value 0 for x after we had synchronization. Now, a word before we continue, we do not account for load buffers. That means that if the first thread reads the value of x, then stores the same value to y, and the second thread reads the value of y and then stores 1 to x, well, this is allowed by the C11 standard. We forbid this kind of behavior, and indeed no previous work handles this kind of C11 behavior where we allow PORF cycles. And this is similar to the repaired C11 memory model. And the reason we forbid this is that it leads to the infamous out-of-scene error problem. And this is still an open problem with the standard, and work is done trying to repair the standard in order to allow behaviors that the hardware may exhibit while still forbidding the out-of-scene error problem. Now, what is robustness? Robustness means that all the graphs that are reachable by the program are SE consistent. And by this we mean that there exists some total order that contains all the order relations of the graph for this specific graph. And this is a formal definition, so let me demonstrate this with two examples, where if we have the same message passing example we had earlier, this graph is SE consistent, since we can linearize all the events taking place in the graph, namely starting by writing 0 for x and 0 for y for the initialization. Then the first thread is going to write 1 to x and 1 to y, and finally the second thread is going to read the value of 1 for y. Now, multiple linearizations might exist, and we only require that at least one exists. And specifically in this example, we can swap the two initialization events since they have no order between them. And this would provide us with a different linearization of the events in the graph. On the other hand, this graph is not SE consistent, since in order for us to read the value 0 for x, we require it to happen before we overwrite the value with 1 in this event, which is executed before we write the value 1 for y, which is executed before we can read the value 1 for y, which is executed before we read the value of x. So we have this cycle, and therefore this graph is not SE consistent. Now, So we show that robustness against C11 is decidable and p-space complete, and we do so by a reduction to reachability under instrumented SE semantics. So let me say a couple of words about the proof. We identify the need of only finding a minimal robustness violation. That means that if we have some graph that is reachable by the program that is SE inconsistent, and this is going to be enough for us. And by minimal, we mean that the graph before that is SE consistent. And since this graph is SE consistent, this means that we have an execution of the SC machine that can reach the same program state. Not necessarily by taking the same order of steps, but nonetheless achieve the same program state with the memory of the sequential consistency machine. And we know that the C11 machine can take another step, while the SC machine cannot. And we identify a finite set of properties that allow us to identify exactly this kind of behavior instead of saving the entirety of the execution graph. We only store a finite set of properties in the instrumentation. So let's see how it happens. Considering again the message passing example from earlier, the final graph is not SC consistent, but the graph before that is SC consistent. This means that we have an execution of the SC machine that reaches the same program state. In this example, it actually took place using the exact same order of steps, but this is not necessary. And with the instrumentation, we identify the fact that any execution of the sequential consistent machine is going to have to read the value 1 for x from this side. But under C11, it is allowed to read the value 0 from the initialization. And therefore, we identify a robustness violation. And the crux of the contribution is that we identify a finite instrumentation that will allow us to monitor precisely this kind of property. The instrumentation itself is quite heavy and complex, and you are welcome to look at the paper to read more about it. This summarizes the first contribution. Now let us move to the second contribution. It is related to the use of relaxed reads for doing speculative reads, which poses a challenge to the approach of verification using robustness. A challenge with relaxed speculative reads that was not there with the use of release acquire speculative reads. We encountered this challenge when we were trying to verify seclock. So let's discuss this example. Seclock is an efficient readers-writer lock that is extensively used in the Linux kernel. It makes use of speculative reads, which means that it speculatively tries to read the values protected by the lock, and assuming that it is going to read good values, and therefore lowering the synchronization overhead on the good case. And if the values were actually, afterwards, it verifies that they were actually good. And if they are, it proceeds to use them. If they weren't, then it simply discards them and tries again. And the standard robustness criteria are too strict, as we will show shortly. And our goal is to find a weaker robustness criteria to verify seclock under C11, where we will still keep the property that we want, that if we have robustness and verification under sequential consistency, we will achieve verification under the weak memory model, namely C11. So before we proceed, let us consider seclock when it is run under sequential consistency. For the sake of the example, assume that we are going to have a single writer and C is a thread local scope variable. When the writer is going to write, it proceeds by writing the next sequence number, and this value is going to be odd to indicate a new transaction is taking place. Then it is going to store all the values that are to be protected by the lock, and finally it is going to finish the transaction by writing the next even value as a sequence number. The reader is going to read the current sequence number, and if the value is odd, that means that the transaction is taking place, and it simply tries again until it can read an even value. Once it read an even value, it proceeds to speculatively read the values protected by the lock, and finally it is going to check the sequence number again. And if the values differ, that means a transaction took place while the reader was reading, and the values should be discarded and the reader should try again. Otherwise, the speculation was a success and the values are returned. In 2012, Ansbaum ported this seqlock to C11 and made a couple of observations. The first observation is that the variables that are protected by the seqlock should be atomic and not non-atomics. And for efficiency, the accesses should be marked as relaxed. Second, we require a fence release after the first sequence store, and the second write to the sequence number should be a release write. And on the reader side, we require a fence acquire after reading the sequence number for the first time, and another fence acquire before reading the sequence number for the second time. And even though this implementation is correct, it is not robust because of these speculative reads, as we are going to show shortly. So let us consider this use case. The writer is going to write twice, and we are going to have a reader that is going to read once. The writer starts by writing the value 1 as an odd sequence number to indicate a transaction, executes fence release, and writes the values 1 to x and y, which are protected by the lock. Then it finished the transaction by writing the value 2 as a sequence number. Next, the writer is going to initiate a new transaction, writing the value 3 as a sequence number, and execute a fence release and write the value 2 to x. Now the reader is going to execute. Since no synchronization happened yet, the reader is allowed to read the value 0 for the sequence number, and the value 2 for x from the final write. But because this read does not incur synchronization, it is still allowed to read the value 0 for y from the initialization event. And this is not a problem, since thanks to these fences, it is going to read the value 1 as the next sequence number, and since 0 is different than 1, this speculation is going to fail and the values are going to be discarded. But it is not robust because we have this induced relation where in order for us to read 0 for y, it has to be executed before y is overwritten with the write of 1 to y, which is executed before we write the value 2 for x, which is executed before reading the value of x for reading 2, which is executed before we read the value of y. So again, we have this exact same cycle that we had before. And under sequential consistency, there is no way to return the values for multiple writer iterations like this. And we see that the standard notion of robustness is too strong to allow verification of such programs. And in fact, if we consider a stronger robustness notion based on reachable program states, it is still not robust, since at this point we have registers holding the value that was read as 2 for x and 0 for y, which is not a reachable program state under sequential consistency. And in other words, what happens here is that the violation of sequential consistency are only in speculative reads whose values are actually discarded. And this is the reason we can fix this graph by reading the value 1 for y from this write, and the rest of the execution is going to be identical. We are still going to read the value 1 for the sequence number that is going to be different from 0 and discard this execution. So we are basically not going to be able to tell the difference if we fix the graph. And this leads us to our second main contribution, which is a weaker notion of robustness. And the formal definition is available in the paper, and here I just give you the intuition, where all the graphs that are reachable by the program under C11 are AC consistent if we ignore some read-write orders when the read value is never used. And for those of you who know the model, it means that we only consider FR edges that start from a read that has an outgoing dependency. And even though it is weaker, we still maintain the property that we want, where we can reduce the safety verification under the weak memory model to a safety verification under sequential consistency plus verification of observational robustness. And we can use the same tracking mechanism that we've seen earlier by augmenting it with a taint tracking mechanism to track which reads can be ignored. And the full details are available in the paper. And we basically augment Rocker to support input of being programs with C11-like atomics and non-atomics. And instead of creating verification problems that check for robustness, or we create a program that checks whether the program is observationally robust or maybe not observationally robust. Where we mean by this that this method is sound but not complete. But for all practical examples, that they were either correctly identified as observationally robust or not observationally robust, and only some contrived examples that are observationally robust are incorrectly reported as not observationally robust, but again, they are only contrived examples. Now, let me mention a word about the proof, that the correctness proof here is much more challenging. We may reach a graph that has many violations of sequential consistency, and we need to fix it gradually in order for us to get a graph that provides us with a witness for the non-robustness of the program. Finally, we benchmarked Rocker in order to see the amount of time it takes to verify robustness for programs. And indeed we saw that SecLock is correctly identified as not robust, but is observationally robust. In addition, an implementation of Peterson's mutual lock for C11 that was previously deemed to be correct was actually found by us to be incorrect, and we propose two possible fixes in order to restore the correctness of Peterson's mutual algorithm for C11. And the problem with the earlier proofs for this implementation was that they proved a different property than the one we actually require for correctness, and they only considered a single iteration of the lock instead of multiple iterations. To conclude, we proved that robustness against C11 is decidable and space complete, and developed a verification method and a tool called Rocker that allows us to check for robustness of the program, where the input is C11-like atomics and non-atomics to our tool, which creates verification problems that assume sequential consistency and do not actually require the weaker hardware model. And these problems are fed to the speed model checker and allow us to check whether the program is robust or not robust, or whether the program is observationally robust or potentially not observationally robust. The tool is available on GitHub and you are welcome to play with it. Thank you.